Hi, everyone. Welcome to episode number 3. I hope you're doing well. So I just want to recap a bit about what's the first two episodes were kind of about. So, episode 1 was kind of diving into the fact that Einstein was this kind of link between Newton and kind of a new theory of gravity, specifically about motion. Um, and one of the big conceptual differences between them is that Einstein says that you cannot go faster than the speed of light. So that's a really big thing. And from that, he essentially deduces a bunch of things that we'll hopefully get into at some point. Episode 2 was talking about this thing called action at a distance. And maybe if it wasn't as clear, essentially what the whole problem boils down to is gravity in Newton's definition. There's nothing about his definition that tells you how gravity actually works. So, like, for example, if you have a ball over here, and then you look away and then it goes over here, your assumption is that someone came over and pushed it, right? Someone had to do something to that ball. And you could say, oh, well, you see someone walking away from it. Oh, there's the person who must have pushed it, use some kind of force, like kicked it with their foot or something. Similarly, like I have a container over here. When I'm lifting this container up, I am the one who's putting work on this container and I'm causing it to go up and down. Like I'm the one doing this. I'm the one doing, actioning this kind of. So the thing is that action at a distance. One of the things was, how does this actually get transmitted? How does gravity actually, flow from me to you? Like what does it? It's very mysterious. And so that's why I mentioned a quote last time about this kind of absurdity of the fact that it appears as though nothing transmits gravity from person to person. So anyway, for episode number 3, I wanted to focus on something a bit different. So this is one of the big conceptual things that a lot of people actually do every day, and they don't really know. And so I thought it would be cool to talk about this idea called generalized coordinates. So, what are generalized coordinates, and how at all do any of us implement those every single day? So, I want to just give an example, and I have a whiteboard here. I don't know how well this is going to work, but I just wanted to show this kind of simple image. I know this is very awkward, but just bear with me. So, on this, I've just drawn me, some distance here, 3 meters, and then this is my trash can. So, like many people, we experience life from our own viewpoint. I experience it with my eyes, and I see the world. And when I talk about how far away things are, I constantly refer to myself. So, like, if someone asks me, "Well, how far away is Japan?" I say, where am I?" And then I say, "Where's Japan?" And I say, "From me to Japan, it's X distance." Similarly, like when you walk around your house, or if you're at a hockey game or something, you're going to say, "Oh, there's that player over there. He's about 100 meters away," or something like this. So you are constantly referring to yourself in all of these situations. You're the one that's saying, "I'm here and that thing is over there." So what are you doing implicitly when you do that? And this is where your teachers in school, when they talk to you about this idea of an origin, they typically say, "Oh, where's the origin on this graph?" Those kinds of things. So in your mind, you're probably thinking the origin is 0, 0. It's where 0 is. And the best way to think about origin is you. You are the constantly making yourself the origin in your day to day. So when we talk about coordinates, what are we really talking about? Coordinates are a way of describing essentially like some geometric way of people, like things being far away from you. And this is, again, if you think about it in terms of your horrible memories of math and high school and university, you're going to think about it as being this brutal thing. When they ask you to measure the distances between things and those kinds of things, it's a horrific image, but I want you to forget all about that. I just want you to think of, in your day-to-day life, you never have any issues saying how far away things are from you, or at least estimating how far away things are from you. That is a very natural thing. And even though you can represent how far away something exactly is from you, and it goes into this 3-dimensional math and blah 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 blah, you're very good at saying, like, well, I think this is a meter away from me or something like that. It's very intuitive. So the whole point here is, what is a generalized coordinate then? So what is a not generalized coordinate? A not generalized coordinate is what we do. We constantly go around and we say, my perspective is the only perspective. And what we actually are doing in some weird way is we are the reference point. We are the origin, which is where this term comes from. We are the origin constantly of what you can think of as a coordinate system. So I want to give this example. So in this example, I have me and I have my trash can. Now, in my day-to-day life, I'm constantly referring to myself. I'm constantly referring to me. It is always about me. However, what if, it wasn't all about me? Because right now, essentially what me is this origin point. It's this point 0, 0. And everything is referenced to this, to me. It all has to do with me. So when you ask, how far is the trash can? You're not saying, well, considering the perspective of my door, the trash can is 3 meters away from Dean. No, that's not what you do. You actually say to yourself, that looks like the trash can is 3 meters away from me. That is what you're constantly doing. And what you're doing is you're referring to everything in reference to you, which is what the origin is. It's this 0 point. It's this point of reference for everything around you. So what I want to kind of display here is, well, what is a generalized coordinate? That is something that is important to understand, what a generalized coordinate is. And maybe I'm just going to draw some pictures here to make this clear, what I mean by a generalized coordinate, especially just specifically in 2 dimensions, which I think are pretty intuitive to most people. So I'm going to introduce a third person in here. I'm going to introduce a stapler. So obviously these are not, real objects, but I just want to talk about what a generalized coordinate is. So I'm just going to throw some numbers in here. This might not actually be real, but anyway, it's fine. It's not going to be real. Don't worry about it. And we're not going to assume, I'm going to make this not look like a right triangle. I don't want to throw people off. So this is 4 meters, and let's say this is 7 meters or something. Okay. So what I'm going to do here is I'm going to redraw the origin. See, the origin used to be you. It used to be me. But now you can see in this drawing what has changed. So this is the same drawing as before. So you can see my trash can and you can see me. I'm still 3 meters away from the trash can. But now you have to ask the question, who is measuring this distance? Who is the person measuring? And so this picture is actually a coordinate system where the origin is a stapler. The stapler has eyes, the stapler can see things, and the stapler has said, from me, I might be 7 meters from, Dean or whoever, from that person, and I'm 4 meters away from this trash can. But you notice something. Just because now we're measuring from the stapler, nothing changed about the distance between me to the trash can. Nothing changed at all. There's no difference by looking at things from a different perspective here. And similarly, if you keep doing this process where you think about how do you view things from a different angle, you think about your day-to-day life. When people are running by you, it changes, right? Like it looks like if you were looking straight on at 2 people running towards you, you can pretty clearly estimate like how far away they are from each other. But if they just did the same distance and then all of a sudden they go perpendicular to you, where it's essentially, it looks like they're the same person just running along. That doesn't mean anything that in terms of how far they actually are apart from each other, right? So just because they rotated doesn't mean that they're not still that distance away. So what I want to try and get across here is, for the most part in our day-to-day lives, we are the center of our coordinates. We are the origin. We're the origin of the world. Everything is in response to us. And so this idea of a generalized coordinate is to take you out of the center of the picture and then replace that with something more general, which is a general idea of coordinate systems are very arbitrary. Like taking a different perspective of someone else, like taking a water bottle's perspective, it doesn't do anything to how far you actually are away from different things. It just says something different about how far you are away from that, from that container or from my screen. Like it's now referring to a different object. So I might be 1 meter from my screen and my screen is 1 meter from me. But from changing that perspective, the things change, right? So that's kind of the point. So how does this relate at all to to general relativity. So I want you to think about something. So I don't know if any of you take GO trains, but for the most part, think about it this way. So if a GO train is coming by and you're on the platform and you're standing very close to it, you definitely experience this thing where the GO train is going very, very fast. It seems to go very, very fast. You see the glass, it's constantly shifting by you. It feels like the train is going very fast. However, if you were across the street looking at the train looks not to be going that fast. It's still going quite fast, but it's not going as fast as you think it might be. So similarly, if you saw people running from afar, like from a kilometer away, if you looked at people running, it doesn't look like they're gaining that much ground. But let's say they're Usain Bolt, and when you're really close to Usain Bolt, you see him and he's so fast. So there's something there that's a bit different. Now, one of the key ideas here is that you're looking at it from two perspectives. So in one perspective, it looks a bit slower, and then in another perspective, it looks like it's going much faster. So for example, like if you're very close to the train, you think things are going very fast. If you're not, you're across the street, you're at the stop sign or something, you don't think it's going as fast as that person probably does. So why is that important? So this is where this idea of generalized coordinates become in, because we all have our own set of coordinates that we use. Essentially, we're all the origin of our own lives. And so the person across the street has their own origin, and the person standing in front of the train has their own origin. Now, there's something weird going on where one is experiencing this train going by faster, and then the other one is experiencing going by slower. And I'm just going to use this intuitive argument. I'm not trying to explain anything specific. So there's something there that's a bit different. It's a bit strange. And so what is important about this? How does this have anything to do with Einstein? So the main reason this is important is that you have to realize that we have these laws of nature. And so the key idea here is that the laws of nature, these laws of physics people wrote down, they are true no matter what. So for example, like in my house, gravity is not different than it is in someone else's house. When I throw a ball against my wall, I'm expecting the ball to drop. I'm not expecting the ball to, all of a sudden decide to fly out into outer space, right? So, similarly, the person standing in front of the train is experiencing the same exact laws of nature, let's say, as the person across the street. However, they're seeing something very different. So one of the big ideas with Einstein is that in any of these people's perspectives, the laws of physics, or the laws of nature essentially, that we've codified, they should be the exact same. They should actually work in the same way, and they should be valid in what they call in this theory all frames of reference. In all frames of reference, these laws should hold true. And so there's a very mathematical way of going about that. But the key idea here is that the use of generalized coordinate systems, essentially that the fact that you could be, as a person, you could experience a train going by just shifting yourself right, a meter every second or something like this, or you could watch it from a tower, you could watch trains going by from your office building. All these different perspectives of this train moving may say something slightly different, but at the end of the day, the laws that govern that train moving and the laws of nature should be the same to all of those people. So how do you create a theory about this? And that was where a lot of this complication comes in, because you have to have something that is essentially as most general as it could ever be. And so I want to just mention, like, how is this different than Newton? So in Newton's world, there's one coordinate system. So essentially in Newton's world, there is one origin that everyone operates under. So it's not like I get to determine what the origin is. It's like there's one specific center. This thing could be 100 kilometers outside of the atmosphere of Earth. This could be in someone's basement. This could be in a Loblaws. It could be anywhere, but there's one point of reference where everything is measured in reference to that one point, which obviously, to most people probably doesn't make that much sense. But the whole idea here is that it's absolute. It is the most absolute. Everything is measured with respect to one thing. And so in Newton's world, there's only one coordinate system. There's not many, which actually, it sounds non-intuitive, but it actually is. Because again, we all set our own coordinate systems. We all measure things with respect to ourselves, which by that very definition means that I might be, 1 meter from my wall in this room, but you living in a different community are 100 meters away. So clearly there's a difference in our coordinates because I'm very close to this wall, but you're very far away, right? And so this is this idea. So Newton, he has it that, there's one absolute point of reference and there's no way of changing that point of reference. And so it's an interesting thing to think about. If you want, you can look at it online. It's a very weird notion, this idea of a generalized coordinate system, but it proves to be very foundational in expressing the ideas that Einstein had, which, to summarize, is in every frame of reference, essentially in any coordinate system that a person could have, the speed of light is always the maximum speed. No matter if you're accelerating, if you're going faster, if you're going slow, if you're not moving at all. If you had to have the ability to ride on a rocket, and at the same time you were able to set up an experiment, to test how fast light is going, or if you could see somehow how fast light was moving, you should always see that it's going the speed of light and that it's never going faster than that. And I'll leave you with that. That is how generalized coordinates play a role in this huge grand scheme of things. They give the language, the math language, to talk about what Einstein wanted to speak about, which is this idea of, things being curved, and then, these other ideas of clocks and stuff that you probably heard about. This all comes together in this idea of a generalized coordinate. The fact that when you see things from a different perspective, it should never change the physics of it. And that's how I'll leave you. I'll see you in episode 4. Thank you for listening if you got to this point. And I'll say it again, like, subscribe. Please do not dislike this video. Thank you very much. Bye-bye.